Hi, my name is Sydney Mead, and I'm here to give an overview of my honors capstone project, which deals with creating a chess engine from scratch. So to start off with here, the goal of the project was to create a chess engine that can store board state, explore possible moves, and use intelligent heuristics to efficiently calculate best moves from a given position, and then interact with the GUI to provide a playable experience for users. So in order to maintain board state, bit boards were used, more specifically bitboard encoding. And so this allows us to efficiently encode board state, more specifically piece state and where on the board pieces are. So for example, this row of pawns down here, you can see that this would map to a 64-bit unsigned integer with a row of ones indicating that the pawns are occupying that row. And so we'd have 12 of these for each piece, black and white pieces included. And so that is how we maintain our board state. Next, we can talk about efficient sliding piece move generation. And this allows us to calculate sliding piece move generation in O of 1 time. On the traditional way of generating sliding piece move generation is you start from a square. So for example, if we're a rook, we can start here at this 0 on d4. And you can see like we could go and check like in each direction, are there blockers? So for example, if we go up 2 squares, we see a blocker there on d6. And we do that for each direction. And then we do this iterative process in game as well. What efficient sliding piece move generation allows us to do is do this efficiently in O of 1 time. So for example, for a blocker configuration here, we would multiply this by a magic number, and this magic number is guaranteed to give us a unique hash for each blocker mask. And then in this position, represented by this hash key, we would actually calculate the allowed moves. And so you can see this would be the allowed moves for that rook on d4, given this initial blocker mask. Then when we want to check in game, we take the blocker mask, multiply again by the random number, the magic number, and that would give us our key to index the allowed moves given that blocker mask. So that can be done in O of 1 time through a simple multiplication process. Um, Next, we have actual move generation and move search. And so this can be done using Negamax and optimized using pruning and move ordering, which I'll discuss later. And so the idea behind Negamax is we're representing a two-player zero-sum game. It's also very similar to Minimax with just a slight optimization made. So I can walk you through a quick example of how Negamax works. So for example, let's just say we start here with our 3. And initially, we don't know like what the best move is, but we're in this position as white, and let's assume that the engine is making a move for white here. And so we would search down and look for moves. So we'd come down here, and then we would come down here, and then we'd see this 3. And this would get sent back up as it's the only move available for each person. But since we're doing a depth-first approach here, we would just go to 6 as the next node. So we'd come back up and then go down to 6. And since we see 6 here, we're choosing a move for black here. And black seeks to minimize the position evaluation. So once it gets down to, for example, 3, we statically evaluate the board, and that returns a evaluation for white, a positive evaluation for white. If this is like a negative number, that would be a good evaluation for black. So yeah, white seeks to maximize and black seeks to minimize. And so given that information, we can see that like black is not going to take this path and give a worse evaluation for itself. It's always going to take this 3 here. And with that idea in mind, we can come back over here and we can go down the same path. We can see that now black can force a move of 2 if white decides to go down this path. So if black can force a move of 2, then white doesn't want to go down this path, because if they go down this path, the worst they can do is 3, whereas if they go down this path, the worst they can do is 2, so it's much worse. Let me go back here. And so given that information, we can just not search these. And we can just not search these because white will never go down this path. There's no reason for white to do that. And so again, we can follow this logic down here. Initially, it's a 4, so black is forced to play a 4. That would be good for white. But then as we search further, we see that they can now play a 1. And at that point, we know white's also not going to take this path for the same reason, because if they take this path with the 3, it's much better for them. So they never even take this. And similarly, we can prune this branch and not have to search it. So that is the idea behind negamax pruning. It works the same way for black. Like black's not going to consider moves that are worse for it either. So there's some parity there as well. In addition to this, we also do move ordering as another heuristic. And so this kind of dictates the way we order moves when we're checking them. So for example, we look at capture moves first, specifically capture moves made by lesser pieces. So for example, this pawn attacking the knight would be checked before this queen attacking the knight. And then both of these capture moves would be checked before a more passive move like white's pawn moving up 1 square. And so this is basically to help with negamax pruning. When you order moves like this, you can kind of cut down on a lot of the branches you need to check. In other words, you increase the pruning that you allow for your engine. And so, yeah, the general reason for this is because capture moves are generally either very good or very bad. So you kind of are using heuristic to hopefully prune more branches as you search. And then given these optimizations that I just explained, so pruning and move ordering, and the combination of them, we can see the optimization results here. So for these two optimizations, I looked at it from an opening position and also a position with more capture moves, mainly a more specific good capture move. So for example, this knight can attack this square on f7 and fork the queen and rook. So that would be like a very strong candidate capture move, which with move ordering would be explored faster. And so we can see the percent of original nodes searched after optimization from depth of 6 in both of these positions. So for example, in the opening here, um, after pruning, we're only looking at 7.5% of the original nodes searched. So that would be without any optimization. And then it's a similar value for the move ordering with 6.5%. So the move ordering does take it down a little bit in that situation. And then the real difference comes here, where we can prune based on the from the capture position, and this results in a much, much, much less um, amount of nodes searched at only 1.7% of the original. And pruning and move ordering helps a lot here too, bringing it down to 0.1% of the original nodes. And so we can see from these that these two optimizations definitely decrease the amount of nodes searched and really help the program calculate moves and best moves efficiently. So these were two optimizations that I made to get the engine to work a little faster. And I found with these two, it could almost easily calculate the depth up to a max depth of 6 and find the best move in almost any position in the game, excluding a few positions in the mid game where there's many, many moves to consider. So yeah, that pretty much wraps up my project. Feel free to leave any comments down below if you have questions, and I'll try and answer them. Thank you so much.